When discussing the water content of a soil, we'll be looking at some additional terminology other than what we've already mentioned. We'll be looking at terms like field capacity, wilting coefficient, hygroscopic coefficient, and one which does not appear on this particular graphic, but on the next graphic it will show up, and that's called the gravitational potential or coefficient. In looking at this first graphic, when we apply water to the surface of a soil, we do not partially wet soils, but they become completely saturated as water flows through those pore spaces down in the soil profile. So at saturation, we essentially have 100% of the pore space volume in the soil occupied by water, and of course there is no soil atmosphere or soil air in there. This would be a non-desirable state for the growth of plants, since of course roots of plants do require free oxygen in the soil atmosphere for growth and development. But as soon as we stop applying surface applied water, not all of the water out here in the center of those pore spaces can be held against this gravitational pull. So what we then refer to as the free or gravitational water will continue to move down in the profile, allowing some airspace to be regenerated in these soil pores. When all of the free or gravitational water has moved out, the maximum amount of water that this soil can hold against the pull of gravity is referred to as the field capacity value for that soil. Plants will utilize water from this level down to what is referred to as the wilting coefficient, or the wilting point. The wilting point being that level of water remaining in the soil, and you'll see that it's just a film around the individual soil particles, that we don't have a lot of water out here in between pore spaces like we do at field capacity. That water, which is held very closely by these soil particles, is very, very difficult for the plant to withdraw. And we'll actually see more water loss from the plant than we see uptake from the soil, and that's why it's called the wilting point. At this wilting point, or wilting coefficient, we would have a small portion of the water that's left in the soil that was held there initially. So we see an increase in air volume and a decrease in the soil water volume, within this representing the pore space in the soil, and this representing, of course, the solids or the mineral and organic matter particles in the soil, if we're looking at this on a volume basis. At the wilting coefficient, there is still a little bit of usable water there by the plant. Of course, we don't want to force the plant to utilize that if we're given an option. But shortly after we reach the wilting coefficient, we will then reach what is called the hygroscopic coefficient. And it's illustrated here as being a small amount further down. Hygroscopic water is that water that's held so tightly by these soil particles that it's not going to be absorbable by the plant at all. So we start out with all water held against the pull of gravity as being field capacity. Plants utilize water down to the wilting coefficient fairly readily, and then water held even beneath the wilting coefficient is called hygroscopic water, and it's water that plant roots are not able to withdraw from those solid mineral particles and organic matter particles in the soil. Now, under normal circumstances, in most soils, we have about 50% of the soil volume occupied by solids, and this is on a weight basis here, so it's not really representative. But about 50% of the soil volume is occupied by solids, and about 50% is occupied by pore space. And if we look at the length of this bar, that's pretty well represented here, about 50% solids, 50% pore space. At field capacity, we may have half of that soil pore space occupied by air and approximately half by water. At the wilting coefficient, we might be down to somewhere in the neighborhood of 20% of the soil pore space occupied by water and 80% by air. So really, between field capacity and the wilting coefficient, this level of water held in here is therefore referred to as available water. Available in that plants can take it up, utilize it for growth, development, transpirational loss, etc., without being significantly damaged as they reach the wilting coefficient. If a plant reaches a wilting coefficient and water is not resupplied to this soil in a very short period of time, those plants will not recover even after water does become available to them again. and that would be referred to as the permanent wilting point. Permanent wilting point indicating irreparable damage to the plant. That plant's going to continue to lose water due to transpiration, even though the rate of uptake from the root system can't keep up with it at this wilting coefficient.